Oh, at last, you're here. Where have you been? Let's go. Hi there everyone, welcome back to the channel. Andy Malone, Microsoft MVP and Microsoft Certified Trainer. This week we're going to take a look at Cryptography Made Simple Part 2. We're going to take you even deeper into the world of cryptography and understand how it works and what it can do. And just to say that this is part 2 of a 3-part series, so join me next time as well for the final episode in this segment. As always, if you enjoy what you see, go ahead, click on that subscribe button up there, ring that bell, and you won't miss any future postings. And as always, we welcome your questions, your feedback. Pop them down below. I really appreciate it. So, are we ready to begin? Let's take a look. Okay, so part 2, Cryptography Made Simple. Right, so in this session we're going to continue. We're going to talk about the controversies of cryptography. Now everybody is under the illusion that just because you can't break the cryptographic algorithm means that it's unbreakable, which is not necessarily true. We'll talk about the different cryptographic suites that the National Security Agency support. We'll talk about modern crypto algorithms. Specifically, we're going to focus in this session on understanding symmetric cryptography. And also, most importantly, we want to know how it actually works. So let's take a look. First of all then, cryptography or kryptos means hidden secret or writing. It is the practice of studying techniques for secure communications in the presence of third parties or adversaries. Okay, essentially what it means. Now, given that, we automatically assume because it's encrypted that it's totally secure and it's safe. And in most cases, I'm afraid this is just not true. It doesn't prevent the deletion of the data. So if you had a laptop that was stolen, for example, the good news is the chances are your data on the laptop is secure, but the laptop itself, of course, is, they just need to wipe the disk and they'll get access to it. There's absolutely no proof, actually, that the commonly used secure ciphers are actually secure. We only assume that they are, but of course, as technology goes on and as we get supercomputing and so on, all of that kind of stuff, then it's going to be easier and easier to break these codes. Many people out there consider that security of a cipher is based on arrogance. So we assume that if we can't crack it, then the other side can't crack it either. What about future technologies? So, there's lots of future algorithms starting to come out. Are they actually truly future-proof? And also, cryptography provides kind of a false sense of security, I suppose, especially if it's badly implemented. Now, in many places around the world, you have to be very careful because there are stringent government regulations governing how cryptography works. So again, import-export restrictions and so on. So for example, if you buy a new PC or a new laptop or a new piece of technology, I'm sure you've seen it, it's in the terms and conditions of the sale. You can't go off and ship that to the likes of North Korea or something like that. Now, the reason is because it's a dual-use technology. So they treat it the same as a weapon. Also, encryption is actually prohibited in some countries around the world and can actually, you'd get a prison sentence. So you have to be careful, in other words. Now, back in the 1970s, DES, or the Data Encryption Standard, was one of the first commercially available cryptographic algorithms. And at the time, when IBM released it, the National Security Agency said, yeah, we better look after that for you and just make sure that it's of good quality, I'm sure. So nowadays, all cryptographic algorithms that we use in the West are essentially I suppose, and looked after by the National Security Agency. Now, I am not saying that they've got the backdoor keys. I never said that. Okay. So typically the NSA suite of algorithms, there are 3 of them. So Suite A, Suite B, and Suite C. So Suite A contains algorithms that will typically never be released, whereas Suite B are the suite of algorithms that we use today. Most of them are free of charge, of course they are, and they're pretty much unclassified and easy to use. All right, examples of these include the Advanced Encryption Standard, or AES, elliptic curve cryptography, and this is used in the likes of digital signatures, and also things like Diffie-Hellman. This is used for key agreement, and secure hashing, which was that one-way hashing algorithm that I mentioned in the last session. Suite C, you'll notice here, is full of experimental algorithms that maybe will be released in the future. Okay. So when I said Suite A, if any of you have done any kind of military work or military service, you'll recognize, I'm sure, some of the names on this list. These are obviously protecting important things, like, for example, submarine communications, military radio communications, and so on. And typically these contain classified algorithms that would not normally be released, at least not for a large number of years, or a long number of years anyway. So when we talk about cryptography, modern cryptography can be broken down into 3 types: symmetric cryptography, asymmetric cryptography, and hash functions. Symmetric or secret cryptography, secret key, is exactly that. It uses a single key for both encryption and decryption technologies. And examples of tools that use this: BitLocker, Microsoft's BitLocker. Great for encrypting large volumes of data, but not so good on small chunks of data. So asymmetric, sometimes referred to as public key cryptography, uses one key for the encryption and another one for the decryption. And we're going to cover both asymmetric and hash functions in the final part 3 of this series. So when we talk about the current cryptographic standards, these can be really broken down into different sections. So encryption, you can see symmetric and asymmetric, and also digital signatures. We also have different types of symmetric keys. So for example, that use what we call a stream cipher as opposed to a block cipher. Now, don't worry, all will be explained. So understanding symmetric cryptography. So first up then, symmetric cryptography uses a single key to both encrypt and decrypt, and this makes it suitable for very large volumes of data. Well-designed ciphers are only subject to brute force attacks. So again, if you've seen the movie War Games, you'll remember the Whopper computer at the end of that, where it goes through and it's trying to work out the missile launch secret key by brute forcing every single key combination. This makes it great for data at rest solutions, and this includes EFS, the encrypting file system of Windows, TrueCrypt, or VeraCrypt as it's now known, BitLocker, and it's great for databases, credit card information, and so on. Now in this case, the downside is both the sender and receiver must know the key. And of course, that leads us to the problem of where to actually distribute and store the keys. So symmetric cryptography essentially works like this. So I basically say, yeah, I'm going to encrypt my hard drive. So I use an algorithm with my own private key, and ultimately that's it, fully encrypted. Now this obviously means that anybody looking on, or anybody who steals the disk or gets access to it, unfortunately will not get access to the data. So in terms of security, it's definitely a win-win solution. So it uses a single key to both encrypt and decrypt. So what is the secret then behind cryptography? Well, I'm afraid that you have to look to mathematics. But don't worry, if you're not a mathematic person, and let me tell you, there's nobody less numerate than me. But trust me, you can learn this. So again, I'm going to be doing a series in a few weeks' time on networking. And when we talk about network addressing, an IPv4 address uses a binary format. So a binary format is just a series of ones and zeros. So 1 means it's on, 0 means it's off. So in this case, I'm going to write down the number 255. And you can see that 1 plus, and we work from right to left. So 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 equals 255. Now, computing is all about patterns. Do you see a pattern emerging here? Think about it. 4, 8, 16, 32, 64, 128, 256, 512, 1024. This is how computers work. This is how they think. Okay, so that's the first thing. So I mentioned that binary is either on or off. So if I said binary, it's either on. So can we get 128 into 255? Yes. So 1. Can we get 64? Yes. So 1, and so on. So 1, 1, 1. And add all of these up, it comes to 255. So Andy, give me a number between 0 and 255. So let's say, for example, the number 140. So coming from left to right, can I get the number 128 into 140? Yes. So that's 1. 128 plus 64 is 192. So that's too many. So the answer is no, 0. And so on. Plus 32, no. Plus 16, no. So 128 plus 8 is 136. So yes, 136 plus 4 is 140. And so on. So let me give you another example. Here we have the number 77. So 128 is too many. 64 is okay. 64 and 32 would be too many. But 64 and 8, yes, that sounds quite good. So that's 72. So 72 and 4 is 76. Plus 1 is 77. You understand? Congratulations, you now know binary. So computers work with either it's on or it's off. These are the foundational principles of computing, and thus are the foundational principles of cryptography. Now, you'll notice here, sometimes this is bits of 8. So it moves up. It doubles every time. So 8, 16, 32, 64, and so on. Another numbering system is called hexadecimal, and this is base 16 numbering. So how does this work? Well, we have a number from 1 to 10. So in hexadecimal, it works like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, A. So A means 10. So B would be 11, C would be 12, D would be 13, E would be 14, F would be 15. Now, because I said it's base 16, it's then 10, 11, 12, 13, 14 would be 20, 21 would be 15, 16, 17, 18, 19, 26 would be 1A. 1B, 1C, 1D, 1E. What would be next? So what would be 31? Exactly. It would be 1F. 32 would be 20. So look at 16, the number 16. Yes, the number 16 is 10. So the number 32 is 20. What would the next one be? 16, 32, and on it goes. Do you understand? So that's hexadecimal, base 16. Now, a really important concept in cryptography came with this. It's called XOR, or Exclusive OR. Now, this is considered to be the magic sauce behind many modern cryptographic algorithms. And although initially it looks complex, it's actually really quite a simple principle. So here's my array of numbers again, my binary array of numbers. And what we do is we essentially input two sets of numbers. Okay? So it takes two inputs, so 21 plus 10. Now you can see on the decimal side, on the right-hand side, 21 plus 10, of course, is 31. So what we do, working from right to left, or left to right, doesn't really make any difference, but you can see here that the first digit is 0 plus 0. Now, where you can see 128, obviously 128 for 21 is too many. So the answer obviously is 0. Now, in this case, where two numbers match, it's often called ANDing. So this is often called the ANDing calculation. So 0 plus 0 equals 0. So where the number matches, the answer is 0. So we're looking for numbers that don't match. So in this case, we come to the 16, and you can see 16 has a 1, and underneath it has a 0. So the answer here would be 1. 0 plus 1 equals 1. 1 plus 0 equals 1, and so on. Do you get the idea? So you can see here 1 plus 0 equals 1, and an 8, 0 plus 1 equals 1, and so on. So when you add all those ones up together, the answer should be 31. And that's ANDing. And that, ladies and gentlemen, is exclusive OR. So taking two inputs, two binary inputs, and adding them together. So you can see here 31 in decimal is essentially 1111, or 1F in hexadecimal. Simples. Okay, so symmetric cipher types, there's basically two types. You can either get what we call a stream cipher or a block cipher. The stream ciphers do exactly as it says on the tin. They tend to encrypt in a single byte at a time. So a single byte in one go. So bit, they do it in a stream. Block ciphers are called because they do it in blocks. So they encrypt in blocks of data at the same time. Now, another concept is something called modes of operation. So typically in cryptography, an operation is an algorithm that uses a block cipher to provide confidentiality and or authenticity. A mode of operation describes how to repeatedly apply a cipher's single block operation to securely transform amounts of data larger than a block. So an initiation vector. Most modern ciphers use what we call a unique or random binary sequence, and we refer to this as an initiation vector. And this is created for each cryptographic operation. So it's often used to ensure that distinct ciphertexts are produced even when the same plaintext is encrypted multiple times independently with the same key. And as you can imagine, this is to stop if you discovered the secret to it encrypt one, you then wouldn't be able to break the rest of the code. Okay, block ciphers have typically one or more block sizes, but during transformation, the block size always remains fixed. So symmetric cryptography, some examples. As I said earlier, in 1975, what was happening? So IBM was producing their first computers for the National Security Agency and NASA. And at the same time, obviously, encryption was becoming more and more important. The data encryption standard was one of the first encryption standards in the world. Well, certainly in the commercial world. It was a 56-bit key designed by IBM, and at that time, obviously being available commercially, kind of, the National Security Agency thought, well, maybe we should kind of monitor this, look after them, and if any ongoing development in cryptography is going to happen, we need to make sure that it's done to a suitable standard. Of course they did. However, the DES algorithm, although as good as it was, eventually was discovered that it had quite a number of weaknesses. Now, over the years, it went through different versions, and I'm sure on YouTube you'll be able to watch all those different versions. Eventually being replaced by an algorithm called triple DES a few years later, but ultimately its flaws were discovered, and eventually, by the late 90s, it was decided to replace it. So in 2001, there was a major competition worldwide. So cryptographers from all over the world came from far and wide to try and work out the new next generation algorithm. And of course, the winner was an algorithm called Reindoll, which then became the advanced encryption standard. And it was interesting because it had 3 variable key lengths, 128-bit, 192 and 256-bit key lengths. So obviously, the stronger the key length, the more secure the algorithm. Other kind of runners-up or other entrants included Twofish, Blowfish, and Idea, was just to name a few. Twofish was designed by a famous cryptographer in the US, Bruce Snyder, of course. So these were the winners. This was a couple of Belgians. So just goes to show that not just beer and chocolate are the good things to come out of Belgium, but in fact, one of the most advanced cryptographic standards that we use everywhere today in our modern lives. So this was known as Reindoll, and it later became the standard as AES. As I said, it was the winner of that competition. It uses a variable block length, 128, 192, or 256 bits. It basically was labeled as FIPS 197, which is a standard, a cryptographic standard. And again, it became known as the Advanced Encryption Standard in December 2001. And it's free completely for public use. If you'd like to know more about AES, then check out NIST, the National Institute of Standards and Technology. They've got some great white papers on it. Now, just to understand AES, you've got to think big in terms of numbers, all right? So put it like this. You've got 1 in 2 to the power of 61 odds of winning the lottery and being struck by lightning on the same day. 2 to the power of 92 atoms in the average human body. 2 to the power of 128 keys in a 128-bit key. 2 to the power of 170 atoms in the planet. 2 to the power of atoms in the sun. So 2 to the power of 190, wow. 2 to the power of 233 atoms in the galaxy, 2 to the power of 256 possible keys in a 256 key. Wow, that is awesome, isn't it? I can't even think about how to compute that number. Okay, so AES, typically how it worked. Well, it started with a random number and the data is converted into a hexadecimal state array. The AES process, it then uses a complex system over four functions over 10 rounds, i.e. it repeats it 10 times. And those 4 functions include subbytes, shift rows, mix columns, and add the round key. The final stage involves the actual key expansion. So let's have a look then at how it works. So just looking at the design here, it's mind-boggling. And again, this is just really just for fun. You don't need to learn this, okay? This is just for fun. I just want to show you kind of how it, the thoughts that go in into creating this. So here is a little demo, and this was devised by a gentleman called Enrique Zabala a few years back, and he did this great demo. So let me walk you through this. So this is the Rain Doll cipher. Now, what we've got, this is a 128-bit key, so you can see plain text goes in and cipher text comes out. As I mentioned, you put the data into a random state array, so that we've got basically the state array, and then you've got the cipher key itself. Now, first of all, we go to the encryption process. So we take that state array, that piece of data, and it goes into this process. So basically 10 times. So stage 1 of the encryption process, you can see the cipher key, it goes through those 4 processes 9 times. On the last 10th time, it misses the mix columns out. Why? Who knows? Okay, so let's look at that in more detail. So basically, it does a sub-byte. It takes the number, so 1 and 9 in hex, and it runs it through this state array table. And it substitutes the item, yes? And it does that for all of them. Stage 2 is shift rows. So the first one, it doesn't do anything. The second one rotates by 1, third row by 2, and the third one by 3. So that's shift rows. Stage 3 involves mix columns. And this involves a little bit of mathematics. Again, so it runs through this fancy mathematics. Not enough time to talk about it here. And it mixes those columns up. Finally, it does something called adds the round key. So this is the round key function. So it takes it and it basically XORs that key that we just spoke about. And it then, of course, does that for all of them. So that's round 1. So it does that transformation 9 different times. So, yep, 9 times round 1, round 2, round 3, 4, 5, and so on. Eventually it gets to the 9th round, and on the 10th round, it misses out the mix columns. Okay? And then we have our encrypted output, our ciphertext. Wow, that's complex, eh? So the key expansion for the key, the cipher key, basically is done like this. So in creation of the cipher key, you've got your key in hexadecimal. And it rotates the word for the first column. So it rotates it for the first column. And it then puts it through a sub-bytes. So it takes the number and it looks for the vertical and horizontal point. And it then does what we call an archon function. So it does that for the first column. For the rest of the columns, it just does a straight archon function. Like so. And then that's the first round key. Again, it repeats that rotate word. It does a subbytes. And again, it then does that function. Okay, so you can see it then does that a number of times. And it repeats that, like I said, 10 times. Okay, so 10 times, and what comes out at the end is your cipher key. And there we go. So there we have it. Just a little bit of the controversies of cryptography. We talked about the NSA Crypto suites, suite A, B, and C. Modern cryptographic algorithms. Specifically, we focused here on a symmetric key. I mentioned that that symmetric key is a single key for large volumes of data. And just a little bit of mind-boggling AES animation there, just to let you understand exactly what's involved. So there you have it, Cryptography Made Simple Part 2. Next time, it's all about asymmetric cryptography, public key technology. Exciting stuff. So join me next time. Remember, if you've enjoyed what you've seen, click on that subscribe button, ring that bell, and you won't miss any future postings. And as always, I really do welcome your comments. Okay, thank you so much for visiting my channel, and you stay safe. Take care. Thanks for dropping by. Hope you enjoyed the video. Go ahead and click on the subscribe button and ring that bell, and you won't miss a thing. See you next time.